Dear students, in the last class we have to discuss some theorems of cyclic group and some problems on the cyclic group. Using these theorems, we have to solve some examples and problems. Now we have to continue in these lectures also solve some problems. So, the first problem for this lecture is, suppose G is equal to generated by G is a cyclic group of order 8, then list all the subgroups of G and their orders. So, we have to question is simply say that list all the subgroups of G and their orders. So, we have to group of order is equal to 8, then we have a clearly we just said that since G is a cyclic of order 8, any subgroup of G will also be cyclic, because we have to prove that a group is a cyclic, then its subgroup of a cyclic group is also cyclic. So, if G is a cyclic group of order 8, any subgroup of a G will also be a cyclic. So, the order of any subgroup of G must divide the order of a G. So, possible orders of for subgroups are 1 divisors of this 1, 2, 4 and 8. So, by that theorem we can say the order of any subgroup of G must divide the order of G. So, possible orders of for subgroups are 1, 2, 4 and 8. So, we can construct a subgroups by considering the powers of a G. So, we just suppose order 1. So, suppose subgroup is equal to E. So, G is equal to generated by A to the power 8, and now we have a next is possible order is equal to 2. So, subgroup generated by order 2 G to the power 4 is generated by this is E, and there is a G to the power 4, because we have a and we have a we can just take a G to the power 4 is equal to identity. So, we have to just divide this order of 2. So, just 4 and 8 and 2 is equal to, we have to 2, and 8 divided by this is equal to G to the power k is equal to 4. Next is order is a 4. So, subgroup is order generated by G square. So, we have a 4. So, order is equal to 4, then we have to 8 divides by 4 divides by, so this is 2. So, this is clearly G to E G square G to the power 4 and G to the power 6, and now we have a order 8, and then is generated by G, and that is equal to all the group G, E, G, G square, G to the power 3, G to the power 4, G to the power 5, 6, 7, all this thing. So, we have only possible, these are the 4 subgroups are order 1 subgroup is identity, order 4 group, order 2 group of order 2 generated by G4 is E and G to the power 4, then order of a subgroup of order 4, that is group generated by G square, and then possible subgroups G, E, G square, G to the power 4 and G to the power 6, and now we have a order 8 with this group is generated by G there itself. So, this now therefore, the subgroups of G are, we have said that G to the power 8 with order 1 generated by G to the power 8 order 1, generated by G to the power 4 with order 2, generated by G to the power 2 with order 4, and generated by G to G, that is group of a subgroup of order 8 into this form. So, now this very clear, we have to many examples. Now, we have one more example, we take a problem like this. Let G be a group generated by G be a cyclic group of order 20. Now, found the number of elements of order 4 in G. Now, we have to find that in this G is a cyclic group of order 20. So, we have to find the number of element of order 4 in this group G. So, we start with the order of an element in G to the power k in G is 20 upon GCD of k and 20. So that means we have to k's we have a giving the find the order of number of elements of order 4. Number of element of order 4 means we have G to the power 4 is equal to we have a so we have a order 4. So we need a G to the power order of G to the power order of G to the power is order is a 4. So we just say that by 20 GCD of k 20 is equal to we have a clearly is equal to 4. So we take solving for GCD k we get this so GCD is equal to k and 4 is equal to 5, and since 25 is equal to 4, so GCD of k we have a since 20 divided 5 is equal to 4. So we get GCD of this k and 20 is equal to 5. So we need to find all k such that k lies between 1 to 90, and then GCD of k and 5 k and 20 is equal to 5. So we find all the values of a k between 1 to 19, where GCD of k and 20 is equal to 5. Whenever k is equal to 20 is equal to GCD of this k 20 is equal to 5, then the orders of this group has a elements of a order 4 in we can find in such a way. So we just start the integer k is satisfy this condition, that means are the multiples of 5 but less than 20. So k is multiples of a 5 is equal to 5 and 15, and there is no other multiples of a 5 here. This is clearly between all this value, then is equal to 5, then all the values of a between 1 to 19 which is a multiple of a 5. So this is a multiple of a 5, only two possibilities we have a 5 or 15. So in this case we have take first k is equal to 5. So there are G to the power 5 and G to the power 15 are the elements of a order 4 in G. So this means G to the power 5 and G to the power 15 are the elements of order 4 in G. So we can just check G to the power 5, if we take a 5 and 20 is a GCD is equal to 5, 5 for this again is clearly by this thing. So order of 4 G is order or G to the power 5 has order 4, clearly we can say that order of G to the power k is equal to n and divide the GCD of k and 20, and then we have a order of G to the power 5 is equal to we can take a 20 upon we take a GCD of we take a k is equal to 5 and 20, and then GCD of a 5 and 20 is equal to we have a 5. So this is clearly is equal to 4. Similarly, we take a 15 and 20 again this is greatest common divisor 15 and 20 is again 5, and then G to the power 15 also we have a getting the order of a 4. So there is only possible there is a k is only 2 number of elements of order 4 in G is there is a 2 possible orders is G to the power 5 and G to the power 15 are the elements of order 4 in this group of cyclic group of order 20. So there are only 2 elements of order 4 in. So we have to just complete the solution of a this problem. Now we have to move to the another problem. We have to try to find the in a group G, G to the power 5 is equal to identity, and G H G inverse is equal to H square, and G H are the element of a G. Then we have to find the order of H, and then you have to show that the order of H is equal to 15. So we have a given G to the power 5 is equal to 20, and then we have to G H G inverse is equal to H square. So we start from the G H inverse ka square. So we take a H square is equal to we write into this form. So if H square is equal to this, then we have to write H to the power 4. So H to the power 4 we just say that H to the power 4 can be written as a G H G inverse and G H G inverse, and now you can see we can all the elements of a G and H are the element of a G. So, G inverse H inverse is also the element of a G. So, we just take the group. So, there is property G H. Now, we have a G inverse G, then H of a G inverse, then G inverse G is equal to identity. So, we can write G H identity H of G inverse, then we have a G of H square and G inverse. So, we have a like this. Now, we have to take h to the power 8. H to the power 8 is equal to, we have a write in the form G of H square and G inverse, and we have a G of H square G inverse. Again, this can be written as a G of H square. Now, G inverse G, and then we have a H square and G inverse, and then again this is identity. We can say that G of H square identity H square G inverse. So, we write G of H to the power 4, and then we have a G inverse. So, H to the power 4 is equal to, we have a this, and H to the power 8 is equal to, we have a H to the, or we can just put the value for H square again here. You just write as G of we have a G, and then we have a we take a H, and we have a G inverse and then G inverse. So, this can be written in the form of a, we write into the form of like this. So, this can be written in the form of G square H, and then we have a G to the power minus 2. Similar fashion, in this G to the is to the power 8, we can write in the form of a G, and then we have a H to the power 4 and then G inverse, and then again H to the power 4 is equal to this. So, we can write G square H G to the power minus 2 and minus 1, again G to the power 3 H G to the power minus 3 in this form. So, in this form continue, just I just explain you, H square is equal to this, then H square we have to writing this. So, H to the power 4 can be written in the form of a we have a, let's write G square H G square. Similarly, we can write H to the power 8, and then we write H square this, and then again substitute the value for H square. H square you have a clearly the value of H square, we have a G H and G inverse. So, then H to the power 8 we getting is equal to G to the power 3 H G of minus 3, and we have to in the similarly, we have to go to the H to the power 16. If we have H to the power 16 can be written in the form of this G to the power 3 H G to the power minus 3, and then we have a G to the power 3 H G to the power minus 3, and this can be written as a G to the power 3 H, and then we have a G to the power minus 3 G to the power 3 H of G to the power minus 3, and again this is given the identity element. So, this is G to the power 3, then we have a H square and then G to the power minus 1. Again substitute the value for this G to the power 3 G H and G inverse, and then we have a G to the power minus 3. So, we can write is equal G to the power 4 H G to the power minus 4. And the similar fashion, if we take a square of this, we getting the G to the power 16, and then G to the power 16 means we have to again this is in place of this, we can write into this form. So, we write in the form of this G to the power 32 and G to the power 4 H G to the power minus 4, and then we have a G to the power 4 H G to the power minus 4, and then this can be written as a G to the power 4 H. We have a G to the power minus 4 G to the power 4 H G to the power minus 4, and then you have a G to the power 4, and this is again identity. So, H identity H G to the power minus 4, then we have a g to the power 4 h square g to the power minus 4, again substitute the value for h square g to the power 4 g h g inverse g to the power minus 4. So, we getting g to the power 5 h g to the power minus 5. But also you have a given that g to the power h 5 is equal to identity. So, this means h to the power g, we have a giving this element e to the power 5. So, g to the power 5 is equal to identity. So, g inverse to the power 5 is also identity. So, g to the power minus 5 is also identity. So, we can say g to the power 32 is equal to, we have to say that h, and so this means h to the power 32 is equal to, we have a h. So, this means h to the power 32 is equal to h. So, we can say h to the power 32 is equal to h, and then we have to multiply, this can be written as h to the power 31 h is equal to e into h, and by the cancellation law we can say that h to the power 31 is equal to identity, and this implies that order of this h is equal to, we have a 31. So, we have to show that, that means we have a any element, if we have a this, so we can say since 31 is a prime power number. So, 31 is the least positive integer where h to the power 31 is equal to identity. So, this means order of h is equal to 31. So, we can prove this very simple way that if we have a h is equal to g h g inverse and g to the power 5 is equal to identity, then order of h is equal to, we have a 32. I think this is clear for this. Now, we have to move to the another example problem where they say that order of a b, if order of a and order b are relatively prime, and then this group is abelian, then we can say that order of AB is nothing but is equal to order of A into order of AB. So, if A and B are two elements of a group G, and then such that AB is equal to BA, this group is abelian, and order of A and order of B are relatively prime, then we can easily show that order of AB is equal to order of A and order of B. So, we just take order of A is equal to M and order of a B is equal to N. So, the condition is m and r relatively m and r the least positive integer, so and such that m and r are least positive integer. So, a to the power m is equal to identity and b to the power n is also is equal to identity. And so, we have to show that order of AB is equal to mn if AB is equal to BA and mn are relatively prime. So, we have to assuming that order of A is equal to this m is the least positive integer, order of a B is equal to n, and m and r the least positive integer where a to the power m is equal to identity and b to the power n is also is equal to identity. So, if this is, then we have to show that order of AB is equal to mn and AB is equal to BA and mn are the relatively prime. So, we are starting from AB is equal to BA, then A implies that AB to the power n, we know that AB to the power n mn is equal to AB to the power m is m is equal to A ki power n and B to the power m. So, we know that the property of this AB to the power n is equal to A to the power n and B to the power n, and this is if we have a AB is equal to BA. So, this condition is hold, we know that this is the property. So, AB is equal to BA, then we can say that AB to the power mn is equal to A to the power mn and B to the power mn, and then this can A to the power m to the power n, then B to the power n to the power n, and A to the power we know that A to the power m is equal to identity and B to the power n is also identity. So, e to the power n, e to the power m, and any power of identity is giving the identity. So, a b to the power mn is equal to identity. If a to b to the power identity, then order of a and b are because m and r the m is equal to identity. And now, we show that this is means clearly mn a to the ab to the power mn is equal to identity. Now, we have to show that this this mn is the least positive integer where this is giving the identity element. So, next we show that this mn is the least positive integer satisfying the above equation. Suppose r is any positive integers where ab to the power r is also identity. So, that means ab to the power r is equal to identity and ab to the power mn is equal to identity. So, ab to the power mn is equal to, we have to, so this is r to the power identity, and as ab is equal to ba, so a to the power r is equal to b to the power minus r, we can just take a inverse element. So, this is a to the power r to the power n is equal to b to the power minus r to the power n, and a to the power r m sorry, this is n. So, a to the power r n is equal to b to the power n to the power minus r, and b to the power n you have to just say that is equal to identity. So, this is the identity element b to the power mm. So, we just say that this is can be say that a to the power r mn is equal to, we have to just say that identity. So, a to the power rm is this is sorry n, we just say that it a to the power rn is equal to identity, that means order of a divides by rn, and this implies that m should divides rn, and so we have to use the property of the theorem. So, m should divides rn, since m and r the relatively prime, that is m and n are so r divides mn, this means m divides rn means m divides r, similarly n divides r. So, since m and r relatively primes, m divides r and n divides r, implies that mn divides r, where r is any positive integer. So, ab to the power r is equal to identity, hence ab, order of ab is equal to mn is the same as a order of this a and is equal to b. So, this should be, this is equal to n in this slides. Okay. So, we have to just show that clearly that this mn is the least positive integer when order ab to the power mn is equal to, we have to getting the identity element. So, now we have to move to the another problem which saying that we have to say the prove that any subgroup of a cyclic group is itself a cyclic group. So, if any we have known that if you have a cyclic group, so all subgroups are cyclic, but here we say that any subgroup of a cyclic group is itself is a cyclic group. So, this is, I just say that we have to already prove this. G is Wisdom, H is a subgroup of G, G is a cyclic. So, it constitute elements of the form of a G to the power k, and k be the smallest positive integer such that G to the power k is equal to H. So, we claim that H is equal to G to the power k, and assume that G to the power m is the element of H. Then by the division algorithm, m can be written as qk plus r, and then G to the power by this G to the power m, G to the power m, it can be written as G to the power q k plus r, and this can be written as G to the power q k and G to the power r, and then we can say that G to the power r is the element of a this G to the power r can be written as a G to the power m minus q k, and this is the element of a H, this is also the element of H. So, this whole thing is the element of a H. If this whole thing is the element of a H, then we can say that G to the power r is also belongs to H. And if G to the power r is also belongs to H, then we have to this contradict the definition of a k, since every element of a H is the form of G to the power k to the power q, where q is an integer, therefore, H is a cyclic group. So, this means we can say that H is the if any subgroup of a cyclic group is itself a cyclic group. So, now we have to this already I have to prove that means we have to find the order of a this is equal to, we have a automatically we have to show that order of a is equal to 31. So, now we have to generalize this problems. So, if we have a B A is equal to a to the power m b to the power n for a b belongs to the G, then prove that the elements a to the power m b to the power n minus 2 and a to the power m minus 2 b to the power n and a b inverse have the same order, where m and n are belong to Z. So, we have to condition is this given. If this is happening, then he said that order of a this and order of a this and order of a this is equal to the same. So, we have to prove that all these 3 a to the power m b to the power n minus 1 and a to the power m minus 1 b to the power n and a b inverse have the same order. So, let us start by first one. We have to write a to the power m b to the power n minus 2 can be written as a to the, because we have a, keep in mind a to the power m b to the power n is equal to b a. So, a to the power m b to the power n b to the power minus 2, then now use the associativity here. So, we just write into the a to the power m b to the power n and b to a to the power b to n is equal to, we have to write as a b a. So, b a b to the power b to the power inverse, then we have b a b inverse and b inverse. So, this can be written into a this form. Now, similarly we have to is this form a to the power m n written in the. So, this is, we can say generally say a to the power m b to the power n minus 2 can be written as a b a b inverse and b inverse. Similarly, starting from this second one, so we have to just say that a to the power m minus 2 b to the power n, and this can be written as a to the power minus 2 and we have to write just a to the power m and b to the power m using this, and a to the power m b to the power n is equal to b a. So, this a to the power minus 2 b, and we have a we have to just say that a to the power minus 2 b a. So, we can write in the form of a to the power minus 2 b a inverse and e to the power minus 2. This is can be this can be written in the form of this a to the power minus 2 b a, and this we have to in this clearly this is the same into this form. So, we just write into a this form, and now we have the third one is we have to just say that we know that x y is the element of a G, then order of a x is the same as the order of y inverse x y. So, we have to order of x is the same as the order of y inverse x y. So, we using this property. Now, where x is equal to, we have to taking is a b inverse is this one, and then y is equal to we take as a b inverse, and then a and b are the element of a this G. So, a inverse also the element of a G, b inverse the element of a G. This means a b inverse is the element of a G and b inverse is also the element of a G. So, if a b inverse is the element, b inverse, so we have to in place of this. So, this means order of x is equal to a b inverse is the same as okay, just I just write into this form. We have a say that order of x is the same as a order of y inverse x y. So, we have to take a order of a b inverse is equal to order of y inverse, you have a b inverse to inverse, and then we have a x, we have a b inverse, and then we have a, we can write is equal to y. So, here is have a b inverse, this is order of b inverse to inverse is equal to, we have a know that a inverse to inverse is equal to a. So, this can be written as a b, and then we have a b to the b inverse and b inverse b to the power minus 2, and then we can say that you can see here this one is equal to is this one. So, this is nothing but is equal to order of b of a we can write into, so order of a b inverse is the same as a order of a if order of a this, and this quantity is equal to, we can say that order of a to the power m and b to the power n minus 2. So, we prove that order of a b inverse is the same as a order of a to the power m b to the power n minus 2 is there. So, order of a b inverse, so we can write into this form, and clearly this is equal to this form. So, next we have to try to this one, and then you can see we have a like this. So, we have to taking in this form, x is equal to b a inverse and y is equal to, we have to take a. Then we have again using the property order of x is equal to order of y inverse x y. Then order of x is, you have a clearly you have a order of b inverse, and then b inverse and b to the b square are the element of a g, and then you can say the a square also the element of a g. So, this can be written in the form order of y inverse is equal to a to the power minus 2, and then we have a x b a inverse then a to the power 2, and then you can see this is the same as we have to write in the form of order of a to the power this one a to the power m to the power n minus a to the power m minus 2 b to the power n, and then you can see clearly this a to the power minus 2 b a inverse a square, and this is equal to a to the power m minus 2 and b to the power n. So, we can write into this form. So, clearly we have to say that b a inverse is equal to order of this, and now because we have a condition this, so this we know that the order of an element of a group is equal to the order of the inverse of its element, then there is can be written as a order of a b inverse, we have to using a order of a b inverse is equal to order of a b inverse ka inverse. So, this means we write as by using this condition. So, we can say that order of a is the same as the order of a inverse. So, if order of a is the same as the order of a inverse, then we can say that order of a b inverse can be written as order of a b inverse ka inverse, and now we using the property a b inverse is equal to b inverse a inverse. So, we have a we can just write into this form, this can be written in the form of a this. So, this is order of b inverse to inverse, and then we have a inverse, and this is equal to order of a b inverse to inverse is equal to b and a inverse, and we have to already show that order of a b a inverse is equal to order of a to the power m minus 2 and b to the power n. So, this is we have to clearly we have to prove that, and then we have to show that order of a b inverse is equal to order of a to the power m minus 2 b to the power n, and also order of a b inverse is equal to order of a to the power m b to the power n minus 2. So, generally we can prove that we write order of a to the power m b to the power n minus 2 is the same as a order of a b inverse, and this is the same as a order of a to the power m minus 2 b to the power n. That means, the order of all the threes are the same, and we have to prove this thing. So, now I have to stop today's lecture here, and we have to complete this section of cyclic group today. We have to in this section cyclic group, we have proved some important results. With the help of these results, apply these results, we try to solve some problems on the cyclic group and how to find the order of a element, and then we have to just take a group generated order of the generator and the subgroups, how to find how many element in the subgroups by using these theorems. So, now I hope you have a clear this section of cyclic group and its property. and the next class I try to start a very interesting topic is a permutation of a group. So, by this we have to stop here, and next class we start by permutation. Thank you very much.